Geometry lesson 5-2. We've now spent some time working with perpendicular bisectors and angle bisectors and the relationships that they create with the sides or the angles. And we know that whenever we have a bisector, it's going to cut something in half, and a perpendicular bisector is going to cut that side in half at 90 degrees. It's also, for an angle bisector, we know anytime we're on the angle bisector, we're that equal distance away from the sides. So if we start applying this to triangles, then we would first start talking about the perpendicular bisector of a triangle. If you forgot about the rest of these sides, this side here and this side here, and you just concentrated on one side of the triangle, this would be a perpendicular bisector because that side is exactly the same as that side. Maybe the triangle looks more like this, and you have a perpendicular line that is bisecting that side. Right? So it can be a line, it can be a ray, it can be a segment, whatever, but it's going to be perpendicular to the side of the triangle at the midpoint, in other words, cutting it in half. So without the other two sides, this would be exactly like the last information we discussed, which was perpendicular bisectors. Different triangles actually have different perpendicular bisectors. Now, concurrent lines, when three or more lines, actually, or rays or segments, intersect at the exact same point, then we are going to refer to that as our point of concurrency. So wherever these three lines actually meet, their intersection is the point of concurrency. Just a concurrency is any time you have an agreement. So in this case, the three lines are agreeing on one specific spot. Now, with perpendicular bisectors of triangles, we have three different types of points of concurrency. These are all the same thing. These are all dealing with the point of concurrency, just for the three different types of triangles. One type of triangle we can have is called an acute triangle, where all three angles, talking about this angle, and this angle, are all less than 90 degrees. That's what makes it acute. Anytime you have this type of a triangle, an acute triangle, you will have a point of concurrency that is located somewhere inside the triangle. Now, this is a perpendicular bisector. And because it's a bisector, it means that this side is the same as that side, these are the same as well, and these are the same. So anytime you have perpendicular bisectors that intersect inside, you know you're dealing with an acute triangle. If you have an acute triangle, you know they'll meet inside. If you have a right triangle, then the point of concurrency is going to actually be located on the triangle. This is 90. This is 90, and that is a 90-degree angle. So there are still three perpendicular bisectors. This side is congruent to that side. That is congruent here, and those are congruent because they are bisectors. So a little different. When it's acute, you're going to be inside. When it's a right angle, it'll be on the perpendicular bisector. And that leaves us one more. When we have an obtuse triangle, they will locate outside. So this is one perpendicular bisector. This is another perpendicular bisector for this line, and this is a perpendicular bisector for the longest side. These are the same, and these are bisected. So they will be located outside. Even though this one has the perpendicular bisector going up, and we would typically think it goes this way, it does, but it also goes that way forever, and that would be your point of concurrency. Now, specifically speaking, that point of concurrency has a special name when we're dealing with perpendicular bisectors. We call it the circumcenter. The circumcenter of a triangle is where the three perpendicular bisectors come together. Alright? And what's interesting about that point of concurrency is that they will all be the exact same distance from the vertices. So this is a vertice here, this is a vertice here, and this is a vertice here. Since this is a right triangle, we know the perpendicular bisectors will be located on it. Where that point is the exact same distance to all the angles. So think for a moment. Perpendicular bisectors cut sides in half. And when you cut the side in half, where they come together is going to be the same distance to all the angles. Cutting the sides in half makes me get equidistant to the angles. Is another way you can maybe try to remember that. So that's our point of concurrencies when we deal with perpendicular bisectors. Now, as an example, let's think about if we had a yard that was shaped in a triangle, and we knew that from Z to B was 10 feet. Where is the best location for the sprinkler? If we had a big sprinkler that that shot water all the way to here, and 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 all the way to here, you know, we would have the ability to cover most of the triangle. But we wouldn't be able to cover this part down here unless we had a sprinkler that shot even further, in which case we'd be wasting an awful lot of water. But if we came from down here, maybe we would have enough. Maybe we would be going like this. Well, that might only cover that much of the triangle. From here, we could certainly go down to there, but we'd only be able to cover maybe to this corner. So we'd be missing that chunk. The best place would be at B, because the distance from B is the same here as it is here as it is here, which means this circle that's created, yes, we would have a little bit of overlap here, but our radius of this circle would be centered at B. So our best location is B. The second half of this question, if our sprinkler can shoot 15 feet, is it going to reach all the plants? Oh yeah, because if it goes 15 feet, it's going to go 5 feet past here. It's definitely going to go 5 feet past here, and it's going to go 5 feet past there, which is more than enough to get itself to cover the entire triangle. So we definitely have enough. We would say yes. And this would be option B. Boy, the lag is something today. Alright, that pretty much covers the perpendicular bisectors. We also talked last time about angle bisectors, and we have points of concurrency for them as well. So the angle bisectors can all come together. Alright, all the angle bisectors will cut each angle of a triangle in half, and they will also meet. Where they meet is what we would call the incenter of a triangle. So here's an example. This angle is the same as that angle. This angle is the same as this angle. And this angle is the same as that angle, because the angles have been cut in half. They've been cut in half. That's why they're called angle bisectors. This is called the incenter. Very difficult to remember. Incenters are the angle bisectors. Circumcenter is the perpendicular bisector of all the sides. Concurrency of angle bisectors of a triangle theorem. The angle bisectors of a triangle intersect at a point that is equidistant from all sides of the triangle. In other words, when we are on an angle bisector, we're the same distance from this side as we are from this side. When we're on this angle bisector, I'm the same distance from that side as I am from that side. And when I'm on this perpendicular, or on this angle bisector, I'm the same distance from here as I am from here. If I find the one spot they have in common, then I'm the same distance from all the sides. So this would be the same as this, would be the same as that. Those three sides would all those lengths would be the same. So it's interesting. When we have perpendicular bisectors, we're cutting the sides in half, and we're the same distance from the angles. But when we cut the angles in half, our point of concurrency is the same distance from all the sides. So cutting the angles makes you be equidistant to the sides, and cutting all the sides in half makes you equidistant to all the angles. So it's one way to remember it. Alright? If we had a problem like this, where we had a triangle, a circle inside, and we wanted to know what's the distance from A to L, A to L is this measurement right here. That's going from an angle to the center. And F to L is here. Alright? So what I've done is I've added some more information to help us think about this. These red lines and this blue line. Now the blue line represents the angle bisectors. Alright? The red lines are not the perpendicular bisectors. They are perpendicular, but they're only perpendicular because I'm measuring the distance from the point to the edge. A perpendicular bisector would have been further down here to cut this side in half. So the red lines are not perpendicular bisectors. The red lines are simply the distance that this is from there. Now, if I want to concentrate and find this angle, this triangle's measurement here. So A to D to L, that's a right triangle with legs of 6 and 8. So 6 squared plus 8 squared has to equal the distance from A to L. squared, which means 36 plus 64 is equal to AL squared. 100 is equal to AL squared, which means 10 is equal to AL. Alright, so this distance right here is 10. And what we have figured out is that all these red lines, since we're talking about angle bisectors, all the red lines are the same exact distance, which means from F to L is 8. Just remember, if you cut the angles in half, your point will be the same distance from all the sides. If you cut the sides in half, your point will be the same distance to all the angles. And then you could use some Pythagorean theorem for right triangles if need be.